time. But I'm very glad that you all made it. So Mikhail is really fascinating work on spin mutations and in general looking at the optic and magnetism, magnetic phenomena, and solid times that you have of spin waves, sort of many, many interesting facets. And right now he's in Duisburg-Essen, and he also has a position in St. Petersburg. He actually got his PhD there a few years ago, in 2013. So it's really a pleasure having you, Mikhail, and I apologize in person, and I apologize also for time difference. So I guess it's all yours. Oh, hi, Alex.
Hello.
Yeah. So Mikhail, so you can start.
Okay, good. Yeah.
I'm sorry.
I think I just was waiting. So.
No,
okay.
I mean, I can say more, but that was I didn't want
okay.
to do it every time.
Yeah. Okay. Yeah. So, hello, dear colleagues. Thank you for this possibility to talk with you. So, I am now in Germany. I work in the group of Mikhail Farley in the University of Duisburg-Essen, and I would like to present you not so big presentation about inertia of magnetization in ferromagnets. And this investigation was done in collaboration with Anna Semislava, Ritvik Mandel, and Igor Barsukov. So, oh yeah, here is the outline of my presentation. Firstly, I'm going to give a brief introduction in the inertia dynamics of magnetization in general. Then I will talk about results of investigation of nutation resonance in isotropic ferromagnets. Afterwards, we will discuss inertia in anisotropy ferromagnets. And finally, I will talk about nutation surface spin waves in thin ferromagnetic films. So it's a well-known fact that there are different interactions in ferromagnets, which are appearing at different time scales, and they can be probed, for example, with magnetic field pulses, and with it, spin precession can be investigated at the time scales longer than 1 picosecond. Then if we employ Terahertz facility, then we can probe spin orbit interaction. And next, with laser pulses, one can investigate exchange interaction in ferromagnets and other magnetic materials. And here I will focus on spin orbit interaction, which is a source of magnetocrystalline anisotropy, Gilbert damping, and as it was found recently, it's also a source of inertia of magnetization in magnetic materials. So it was discovered with direct quantum approach, but here I will focus on the classical approach, and within this framework, dynamics of magnetization can be juxtaposed with dynamics of a spinning top presetting around gravity field, and here you can see the animation, how magnetization vector, which is blue here, goes around the effective orientation of the magnetic field in ferromagnets. And this is a very famous model, which was revised by Vigrovi in 2012. He showed that such model corresponds to the non-physical tensor of inertia of the spinning top. And he generalized this model by including the additional components in the tensor of inertia. Basically, now this is physical tensor of inertia of a rigid body. And it leads to additional motion of the inertia, of the magnetization, which is shown here. And this motion is called nutation. So next, based on this tensor, the famous Landau-Dirichlet equation was derived, and then the question arises if the initial tensor was wrong, is this equation, the LRG equation, also wrong? But here the answer is time scales. We can safely use this equation if we investigate slow dynamics of magnetization. But if we would like to investigate fast dynamics, then we need, of course, to improve this equation. And by including the additional term, which is inertial term, and this generalization was done not only with Lagrangian classical approach, but also in the framework of Dirac quantum approach and other theories. They all showed that magnetization also should be described with this inertial LRG equation with this second order time derivative term. And here we have so-called angular momentum relaxation time. And if we investigate dynamics shorter than this time, we have to use this equation. So moreover, here we have eta parameter, which is inertia parameter. And in 2021, nutation resonance was detected at the frequency, which is inverse proportional to this inertial parameter. So now we have that inertial magnetization leads to the additional resonance. Here in the first part of the investigation, we employed this relation between inertial parameter and Gilbert damping, which was proved by Breathing Fermi surface model. And next, in this inertial LRG equation, there are three terms, and each terms can be juxtaposed to a specific vector, which pushes magnetization to a specific direction. So the precession torque pushes magnetization as usual, and it induces precession of magnetization. Then we have this green term, which is damping, Gilbert damping, which tries to make nutation, to make magnetization vector along to the direction of the magnetic field. And next, the last one vector, this is inertial vector, which is has notable component, which is opposite to the precession, and it leads to nutation motion. And here one can see that this position can reduce the frequency of the precession or ferromagnetic resonance. And in addition, the presence of this additional torque yields the nutation resonance. So first, we employed circular variables and found the susceptibility of anisotropy ferromagnets, chi plus and chi minus. And chi plus is responsible for the precession resonance, ferromagnetic resonance, while chi minus shows nutation resonance, and they are in the different frequency ranges as expected. Precession resonance can be detected in the gigahertz range, while nutation resonance is at the terahertz frequencies. And of course, we found some approximation to calculate these frequencies and found that precession resonance is shifted by inertia down. So this is a redshift. And next, we found that this angular momentum relaxation time can be changed, and if we vary this time, nutation line width becomes narrowing. So this is expectable behavior. It means that if we increase a lifetime of this nutation motion, then of course nutation resonance will become narrow and narrow. And then if we employ this relation between inertia parameter and Gilbert damping, then we found that for the specific Gilbert damping, there is a minima at the dependence of notation line width of Gilbert damping for the specific magnetic field. So this is one of the way how one can detect or prove this relation between inertia and Gilbert damping, which was proposed in the framework of Bayesian surface Fermi model. Now let me discuss inertia in anisotropic ferromagnets. In order to do it, we rewrote our LRG equation in spherical coordinate system. We found this relation between eigenfrequencies of ferromagnets and free energy density. One can see that here we have this blue and red terms, which is basically the line width and inertial effects. And if we equal this alpha and eta parameters to 0, then the famous Smith-Badgers relation can be obtained. So it means that we have two approaches, without inertia and with inertia, and we can find the difference between these eigenfrequencies. It's demonstrated here. So the auto approach is plotted with blue dashed lines. And one can see that if we include inertia in our investigation, then the frequency of precession resonance, which is plotted with orange lines. So this is a dependence of eigenfrequency on magnetic field. Yeah, and if we include inertia, then the FMR frequency or precession frequency is reduced. So there's a difference between dashed blue line and solid orange line. And next here we have nutation resonance at the target frequencies with green dashed line. We plotted the estimation of the nutation resonance frequency. And here, if we include anisotropy in our consideration, then the dependence of nutational resonance frequency on the magnetic field can be seen as it's shown here with red solid lines. And here different cases are shown. So for the different orientation of the external magnetic field and for the different magnetocrystalline anisotropy. Next, so we found the approximation for nutation resonance frequencies and the correction of the precession resonance. And here, for example, for the case when magnetic field is applied out of plane for the uniaxial magnetocrystalline anisotropy case, the precession frequency is reduced with this inertial parameter. One can see that here difference between the ordinary estimation of the FMR or precession frequency and this additional term, which is with a eta factor. So we have the reduction of the precession frequency. And next, anisotropy. Yeah.
Can I ask one very quick question for my understanding?
Yeah.
So from what I understand, so far you are solving classical equations of motion.
Yeah.
Can you introduce Hamiltonian and then quantize it?
Yeah, sure. Yeah, it's the question of the next investigations. Of course.
It is?
Sorry. Yeah, we are going to do it. Yes.
Good. Thank you. Mm-hmm.
Yeah. So if you are interested, we can talk about it. Are you working with this Hamiltonian approach, this quantum approach?
Well, I just want to know what the Hamiltonian looks like.
Okay, yeah. Basically, if we are talking about it, then potential energy is included in this. I will show you. potential energy is included in this effective magnetic field, and inertia basically can be took into account with kinetic energy. So this is the way how we can investigate in the quantum approach, like that.
Okay. Mm-hmm.
So yeah, also we verified our analytical investigation with numerical integration. And here one can see this spiral trajectory of the magnetization with small wiggling at the start. So this is a damped Fero oscillation, and this is this small wiggling. This is a sign of inertia of nutation dynamics. And here we calculated Fourier spectrum, which demonstrates two peaks at gigahertz frequency and terahertz frequencies. And here one can see that the theory which is plotted with solid lines is in the agreement with numerical calculations. So, and finally, let's discuss nutation speed waves. So we investigated two cases when waves propagate along the direction of the effective magnetic field, and when wave propagates to the perpendicular direction. Here we included dipole-dipole interaction, speed-orbit interaction, and this investigation was done in the framework of magnetostatical potential, in which we introduced an inertial effect by susceptibility tensor. So we derived the dispersion relations for these two cases. And for the parallel configuration, there are infinity numbers of modes, and here we just plotted the first three modes. One can see that this dispersion relation, which is the dependence of frequency on the wave number. And here with green lines, we draw the precession spin waves, which is shifted by inertia. And with red lines, ordinary precession spin waves are plotted. One can see that inertia induced the shift of the frequency of wave number. And the next, in the parallel configuration, or in so-called Damon-Eshbach mode configuration, we found two effects. First, this is this shift of the precession spin waves, and the next one is we have an additional nutation spin waves, which can be seen as a small wiggling of the magnetization at the almost constant azimuthal angle, because the frequency of this nutation spin waves much is way greater than the frequency of the precession spin waves. And here we can see the dispersion relation for the precession spin waves at the gigahertz range, and nutation spin waves dispersion range at the terahertz range, which is plotted by a purple curve. One can see that these waves both surface and backward with the group velocity, which is way less than the group velocity of the ordinary precession spin waves. And here basically the summary of my talk. So for the resonance cases, we found that inertia-induced redshift of the ferromagnetic resonance and yield the additional nutation resonance. And for the wave case, we obtained that inertia leads to the shift of the precession spin waves down, and it also results in new type of spin waves, which is nutation surface spin waves. Thank you for your attention.
Thank you very much. Thank you very much. You covered a lot very quickly.
Yeah, really quickly. Yeah, I know.
Perhaps too quickly. Are there any questions that anybody wants to ask? Okay, so it's actually so a few people also couldn't come, and one of them was actually Eric Henriksen does experiments. So could you elaborate sort of on what experiments have been sort of done so far in this? And
so experiments, I have these slides. So here nutation resonance was detected at the traverse facilities. Basically, this Telby facilities in Germany. And also, I know that it also was detected with the tabletop laser system. The paper is available at arXiv website. So we have here nutation resonance at frequencies about 0.5 terahertz to the 2 terahertz range, like that. Yeah, so this is experimental proving of this theory.
the spin wave is a prediction. Yeah.
Sorry, may I ask a question, Mikhail?
Sure, yeah, please.
Yeah, maybe very fundamental, basic question.
Yeah, that's fine. That's
my background is we do, first principle calculation. Many cases we study this kind of spin wave or like magnetic interaction. And I see one of your slides, I forget which one you talk about the dipole interaction give you spin wave, and the spin orbital coupling give you this nutation interaction. So in our case, I remember typically, maybe language is slightly different. We don't consider dipole interaction because it's really weak. We know magnetic dipole interaction very weak. We have something like a Heisenberg model. You have an exchange interaction between dipoles, but that one fundamentally seems also from spin orbital coupling because very small, very light element, the spin orbital coupling is very weak. Assume the exchange coupling is also very weak. So that's for example, the TC will be much lower. Yeah, I remember somewhere. Yeah, be cool.
Yeah. So what I can comment about it is that we have to consider dipole-dipole interaction if we work at wave numbers, which basically in this micrometer range. So then if we go below this range, for example, from 10 in the power 6 inverse meter, then of course exchange interaction will dominate over dipole-dipole interaction. So this is the question of wave numbers.
Okay.
Yeah, basically. And this slope, which you can see at the very beginning of this curve, is because of dipole-dipole interaction, exactly.
Okay.
And then it will change. So I can try to draw it, basically. I'll try at least. So
yeah, I see that.
Yeah.
Yes.
So this is it starts 10 seconds about it.
Okay.
Yeah. And this can be detected. I mean this one, this slope because of dipole-dipole interaction.
Okay.
And it's investigated with magnetostatic approach. So that. Yeah.
Well, okay, thank you.
More questions, I will be happy about it.
Thank you.
Yeah, so Vijay, you have a question. I'm sorry, I didn't see your hand before.
Yeah, just a simple question of quantum versus classical. As was asked before, why should I trust these graphs, calculations, etc.? You're going to femtoseconds and there's no mention of quantum mechanics at all.
Sorry, I have not got femtoseconds.
Yeah, so I'm just saying, should I really trust these graphs? Is this calculation really meaningful? or you have to go to the quantum system like Hamiltonian and so on and so forth to introduce some Planck's constant somewhere.
So basically, I would say this is a question of experiment. These curves, which so let me, oh yeah, this curve was investigated and detected with microwave spectroscopy, with Brilliant light spectroscopy, and so on. And in this range, again, I just repeat, classical approach works. Next, if we will detect, or of course somebody in the world will detect this curve, yeah, okay, and it was derived using classical approach, then we can say, okay, it works here, like that. I don't know, if we work with laser facilities and so on, of course, yeah, then quantization of photon energy becomes very important, and or at the temperature when we have this relation, of course, quantum energy and quantization of states and so on becomes very important. But if we have in temperature range, when classical approach works, so this is my thought about it.
Okay, thank you.
Thank you so much.
So any other questions?
Yeah.
Yeah, I completely agree with you. I mean, and also many of these equations of motion are also in the quantum arena. You can basically they're exactly the same as you have classically if you use this for the Keldysh relation and you look at the combinations, symmetric combinations.
Basically, I don't know. I invited Ritwik Mandel. He derived this spin. He derived this relation between inertia and and spin orbit interaction in direct quantum approach. Maybe if Ritwik is here and he can say some words about it. I can see his name on the screen, but I don't know about microphone and so on. Ritwik, are you here?
Yes, I'm here. Can you hear me?
Yes, yes, we can hear you properly.
Yeah.
Yes. So yeah, we did calculate it from starting from Dirac equation, and then what we found out is that of course from Dirac equation, if you expand it semi-classically, let's say, then you can get it normal Schrodinger equation. Then also you can get it all these relativistic corrections of first order and second orders and third order and so on. So you can continue until whichever order you can want. But then I mean, of course, the dominant one here would be the first order, and that is the spin orbit coupling that we know normally. But then we also continued. I mean, of course, then the question was for us whether, I mean, we knew that the spin orbit coupling somehow relates to the Gilbert damping in these cases here. So then the question was whether we could derive something like this Gilbert damping from the spin orbit coupling itself. And then actually we achieved that. We basically derived this from this Dirac equation and then the semi-classical expansions and so on. And then we could derive this Gilbert damping from normal spin orbit coupling. Then we thought, what happens if we go to higher order spin orbit coupling? That would be the second order then in the expansion. Then if you derive that the dynamics, the spin dynamics basically, then we see that leads to something like this inertial dynamics, that m cross d2m dt2. So then we argued that the normal spin orbit coupling that leads to the Gilbert damping dynamics, and the higher order spin orbit coupling, which would be which is basically giving rise to this nutation or this inertial dynamics that we derived here. So then at the end, basically both of them are related, because of course this this normal spin orbit coupling and also higher order spin orbit coupling, they also are related to each other. So in a sense, then of course this eta and alpha, they are also related. And also this is what you will see. I mean, in a sense, if you just do a simple let's say solution of this equation here, this is the second with the inertia now. If you do a simple solution, then you will find that without the alpha, this eta will continue forever. So there will be this nutation, and that will continue forever. But now once you have alpha, introduce alpha, then you see that eta will depend on actually alpha, and then how fast or how small you have the nutation, that will be decided by somehow your alpha.
Thanks.
Does that give some answer? Or
yeah, absolutely.
Actually, very useful.
Actually, I see that Vijay has another question. Vijay?
Sorry?
I see that.
Sorry. I was just wondering if, in a very simple way, you could explain why there are no non-diagonal terms in the inertia tensor I. Is it just a second order, next order, or some next order to be taken care of, or just it is physics-wise so?
Now, I think there are also off-diagonal terms. So what we derived from the Dirac equation was actually tensor. So alpha and also eta, these are basically tensor. But now I think what is done here, when you do not have any non-diagonal element, is just that you take it into the normal principal axis, three principal axis. So that's why you basically diagonalize it. But I think in normally, when you calculate this eta, that they will have off diagonal elements as well. Also in alpha, actually, by the way, alpha is also tensor, and there also you will have these off diagonal elements in general. But of course, this depends on the system. So if you have a particular system, they might not. I mean, the off diagonal elements might have smaller values than the diagonal elements. So then probably you can ignore that off diagonal ones.
Thank you.
Thank you. So Alex, any other questions? This is a nice sort of consequence with your equations, a natural consequence. Yeah. So actually, are there any consequences that you might have also for observables, or for instance, for say currents or things like that?
Sorry, spin current?
Or currents, or something that couples to the mutations themselves. You can actually see in some probes or something.
Probably. I have no answer for these comments, actually. So we can investigate it. So, and basically so for me, one of the goals to talk today is also maybe to give a brief introduction to my investigation, to elliptic investigation, for example, and maybe we can see some and found some way to collaborate. So I'm open to it.
So if I could rephrase my question one more time. Suppose I said alpha and eta equal to 0. So that's very standard. And I know if I have three operators S, X, Y, Z, standard commutation relations, then the Hamiltonian B times S or SZ, let's say magnetic field is in Z direction. So B times SZ reproduces that equation of motion, right?
Precession.
Yes, exactly. So now suppose there's no damping. How would I modify this Hamiltonian to capture the inertial effect? Is that possible?
Probably, but for now I don't have answer.
Okay.
Yeah.
I think it's an interesting question.
Yeah, sure. Yeah. So I have one colleague Boris Ivanov. And we are going to investigate and also your questions in this direction. Probably, so I can send you my email to the chat, I guess.
Yeah.
And we can talk about it, because one of my colleagues also is interested in this investigation, and maybe so sharing some idea or meeting later will be interesting.
Sounds really cool. Yeah.
Thank you.
Thank you.
Okay. Yeah. Just so write me, please, and then let's see.
Thank you. I guess sort of just to repeat what Alex was saying and what you were saying before, and also, so actually, I mean, so you can actually sort of derive many of these equation motions. So of course, the Hamiltonian, and also you can derive them equivalently by looking at the action. And if you look at the action, you also add to sort of Berry phase terms and so on. And if you have just a field, you'll get the first term. You can write the Hamiltonian down, or if you write down the corresponding classical action with the Berry phase term, then the equation of motion will basically be with a gamma non-zero and the rest being zero. And if you have an action that has sort of a non-local in time, so it has a contribution between realization at different times, because at different times, then you'll get the equation of motion that looks like what you have as well. And that you can get by basically, if you have an additional couples to something else, or couples to spin and split realization itself, then by integrating out that additional field, you'll get effectively something that would look like this.
Yeah, I remember your presentation. So about 2 months ago, we was talking about it. Yeah, I remember. Yeah. Thank you for your comments. Yeah, thank you.
Actually, see this one thing in the chat. Oh, was it what you wrote? It's an email you sent, Mikhail. Are any other questions? Okay, I mean, so it's really, I mean, Mikhail, I think you did a great job, but you went a bit fast. So usually you covered a lot of ground very quickly, but the content itself is really fantastic. And so really, thank you very much for this. And
I just was focused on the main points.
Okay. Yes. Yeah. So are there any particular experiments that you think could be done or should be done that you'd like people to do?
Yes. So one of the experiment very maybe can be shown here. So one can find this difference between this ordinary dependence of the ferromagnetic resonance on the magnetic field, which is plotted here by dashed blue line. And if inertia exists and works as we described here, then the frequency of this resonance should be lower. And this difference can be detected at this range, I mean, up to 10 Tesla fields. This is the experiment which will be performed soon here in Duisburg-Essen University. And yeah. Also, one of my colleagues is trying to detect nutation waves with brilliant light spectroscopy. Let's see. He reported that he detected nutation resonance in pernoy films, and maybe with different wave vector, he will find this relation, dispersion relation between the frequency and wave number. So I hope he will be successful. Then we will see a new type of spin waves, which is nutation spin waves.
And actually, do you want to comment sort of also about what happens if you have something other than a ferromagnet, if you have an anti-ferromagnet, or if you have sort of non-trivial
Again, Ritwik can talk about it because he investigates anti-ferromagnets a lot. If Ritwik is here, maybe some words. Because he published 3 or maybe 5 papers about nutation in anti-ferromagnets. I don't know if he available. Okay, Ritwik, are you here now? Okay.
Okay. Have any other questions? Okay, so thank you, actually, Mikhail. I think also for sharing the email address so everybody can, if they have questions or ideas, can contact you. And some people also will watch it back afterwards because they couldn't join. So I guess if there are no further questions, I guess sort of we'll stop here. So thank you very much.
Thank you. Thank you for the possibility. Thanks.